All right, our next speaker this afternoon is Lauren Henson, who joined us this summer from Harvey Mudd. Lauren's been working with Peter this summer, and today we'll hear about their project together, investigating UV nebular emission in the lowest metallicity dwarf galaxies.
All right, yeah, thank you, Gwen, for that introduction. And as Gwen mentioned, I am studying local dwarf galaxies, but the inspiration for my project actually comes from objects at very high redshift, about 6 and above. So looking at the spectra of these very high redshift objects, we're seeing UV emissions in carbon-4, oxygen-3, and helium-2. And these are very unusual emission lines to find in the spectra of objects because they're associated with very high ionization energies. Additionally, the equivalent widths in some of these very distant objects is quite strong or observed quite strongly. So for example, carbon-4, which is shown at the 1548 peak and the 1550 peak here in this diagram, reached equivalent widths as high as 20 to 40 angstroms. And we don't really know what these distant objects are or why they're producing emission that is this strong. So that's an area that we would like to investigate. The theory that we want to investigate specifically is that these objects are actually dwarf galaxies with very young ages and very low metallicities. To explain that further, I will show you a graph by my mentor and one of his collaborators. So this graph shows carbon-4 equivalent width and how we expect it to scale as a function of metallicity. So this red region that you see at the top here is how strong carbon-4 was observed at very high redshift. And each of these green lines that you see along here are photoionization models that are trying to model how this should scale or how carbon-4 emission should scale as a function of source metallicity. The difference between each of these green lines is basically an input into these simulations called the ionization parameter, which basically relates the density of luminous material to ionized gas around the luminous material. So basically, that means if there's more densely packed ionized gas around a star, that is going to cause more excitations and basically boost this type of emission. And we really want to investigate how we can get emissions this strong that we're seeing at high redshifts. So we want to find an overlap between these green lines and this red part of the graph up here. And that is what leads us to this purple region where there's a good amount of overlap, which is less than 5% solar metallicity. That leads into my research question. If we look at young local dwarf galaxies for the sake of comparison, with less than 5% solar metallicity, will we detect UV emission in carbon-4, helium-2, and oxygen-3 at all? And if so, will it resemble the emission strengths found at redshift 6 and above? Okay, so low metallicity can impact emission in many ways in a galaxy, but I'll talk to you about one important way that it could impact emission here. So high metallicity stars have a lot of absorption, which causes something called line-driven winds, which cause them to expel a lot of their material and lose a lot of momentum. So basically, once emission comes from this star, it's going to be like immediately absorbed in this gas. However, in low metallicity stars, more ionizing photons are able to escape and they can fuel nebular emission lines, and that's how we are able to detect them. All right, so next I'll explain to you the two candidates that I looked at for my project. Both of their spectra was taken with the Cosmic Origin Spectrograph, which is on Hubble Space Telescope. As you can see here, both of them are very low redshift, so they're very local to us. This first galaxy here has a metallicity that is 3.6% solar metallicity, and the other one has 2.2% solar metallicity. And also, this last measurement that I have listed here is the H beta equivalent width. I'll explain what equivalent widths are and how we measure them in a minute. But basically, the reason that we have this listed is because it's very hard to determine the age of these galaxies. You would need to know things like star formation history. So we are using this H beta equivalent width as a proxy for age, because this equivalent width will increase when there are more younger stars or fewer older stars. All right, so once I had the spectra of both of my galaxies, I wanted to calculate the equivalent widths in all of the emission lines, carbon-4, helium-2, and oxygen-3. So here is an example of the carbon-4 doublet from the first galaxy, J210455. And the way that I calculated their equivalent widths is by integrating the area underneath their emission lines and dividing it by the continuum level. And basically, the benefit of using equivalent widths to characterize emission strength is because it'll tell you how strong this emission line is in relation to the background continuum of the galaxy. And so here, these dashed boxes represent the area underneath this emission line. And as you can see how equivalent width is the width of this box. All right, once I had the equivalent widths of both galaxies measured and calculated their errors, I wanted to relate those equivalent widths to the age of the galaxy and the metallicity of the galaxy. So these two graphs currently show a bunch of data from Peter and his collaborator, and each data point represents a local dwarf galaxy with relatively low metallicity. As we can see here, there is sort of a general trend line of showing an inverse relationship between carbon-4 equivalent width and source metallicity. And that is in agreement with the photoionization models that I showed previously, which were the green lines on a previous slide. There is a much less clear relationship between H beta equivalent widths and carbon-4 equivalent widths. So there's not like as much of a clear relationship between age and how strong this emission is. But yes, adding my data points to this, we see that this trend continues. And even though that these two galaxies that I've measured this equivalent widths of have way lower carbon content, they actually produce two of the strongest equivalent widths of all galaxies observed locally. So to us, that indicates that we were right in assuming that metallicity is a very important factor in determining the strength of these emission lines. And also that is in conjunction with the fact that they are very low H as well. Now moving on to oxygen-3 equivalent widths. This was actually only observed in my first galaxy, but in general, you can see the same like inverse trend along here. So yeah, there is this inverse relationship between equivalent width strength and metallicity of the galaxies that they come from. Each data point, once again, represents a local dwarf galaxy. And additionally, there is a much more clear relationship between age and oxygen-3 equivalent width. And that's because oxygen-3 is very temperature dependent. And when there's more H beta present in these galaxies, that means there's more younger stars. Younger stars are hotter. Therefore, these are hotter sources. And there is a linear trend between the oxygen-3 equivalent widths and the age of the sources. And then once again, adding my one data point that I got from my first galaxy, we actually see that this drops off quite a bit. It's the value of the equivalent width here is kind of the median of all the data that we have. And we believe that this is just because the oxygen content is so low in these galaxies that the lack of oxygen is winning out over the fact that it's like in a low metallicity region where emission is able to escape. Yes. Also, an interesting fact is that there was no helium-2 detected in either of these galaxies. So here is an example of the spectra that I received from J210455. And as you can see here, there is a very, very clear carbon-4 doublet where we expect those lines to be. And its amplitude exceeds like the rest of the data, the continuum level. However, at where we expect helium-2 to be, which is around 1640, there's like a little bit of a peak there, but it's not very clear if any emission is happening at all. And if there is emission in helium-2, it is much smaller than what we would see in the carbon-4. And so it could just be due to the fact that there is a lot of noise in this data. So currently my ongoing work is to try to determine or kind of constrain the probability that helium-2 is being emitted at all in these galaxies. And yeah, it's just really interesting to us currently why helium-2 would be so much lower in specifically these galaxies out of all the ones surveyed locally, because the only factor that we really changed is like looking at lower metallicity, and helium-2 is not a metal. So it's a curious relationship that it's not really observed here. All right, to conclude, focusing back on that carbon-4 emission, some of the strongest carbon-4 emission has been seen locally at less than this 5% solar metallicity. And so to us, that does indicate that metallicity is a very important factor in conjunction with age for determining how strong carbon-4 is able to be in local galaxies. but it is still not reaching that 20 to 40 angstrom benchmark that we see at high redshift. So that's an area of ongoing investigation. We still don't know how these distant sources are able to fuel such strong lines in carbon-4. One theory could be that ionization parameter I mentioned earlier, which is currently not something that we have the ability to measure. It's just kind of difficult to determine the density of luminous material to the gas surrounding it. But Gwen pointed out to me recently that that's something that James Webb will be able to do in the future. So perhaps we can get a grasp of what those ionization parameters are eventually. But yes, we are realizing that metallicity and age are in fact important factors in determining this emission strength, but we still don't know what these objects are at high redshift and how their emission is able to be so strong. All right, and thank you for listening.
Lauren.
Sorry. Yeah, could you go back to the slide with the emission lines?
So the helium-2 ones?
Yeah, the carbon-4 and helium-2 ones, but the ones where both of them are. Yeah, right here. So where the noise is sort of like eating out any possible emission line that might be there, do you think that this ionization parameter would explain that we don't see helium-2 and would see carbon-4?
I'm not sure, because I think like I don't know if that indicates that there's emission in helium-2 and that's what's hiding it, because I think if there were more densely packed gas and that ionization parameter was an important factor here, we would see absorption, at least in helium-2. I would have to like talk with Peter about that to confirm or deny. But yeah, that's one possibility that we could explore. This is still like very much ongoing investigation.
I see. Thanks a lot.
Other questions?
That was a beautiful talk, first of all. And I have maybe a related question. Are there any other helium lines that you could look at to see if there's any detectable emission or absorption, or is this just the best one to look at?
So this is one that we chose to look at because in the carbon-4 doublet, the UV carbon-4 doublet and the UV helium-2 line, we're often seeing together both at high redshift and especially locally. Like of all the local galaxies that we surveyed, this is like a really unique thing that carbon-4 is there and helium-2 isn't. But we also like looked at like visible ranges of spectra, and it didn't seem like there's like not helium, and that would also be strange if there wasn't like helium in these sources at all. So yeah, this is very much like a point of confusion for us.
Great, let's thank Lauren again.